Desert Storm, 1991. According to Defense News, April 13 to 19, 1992, the U.S. deployed an electromagnetic pulse weapon (EMP) in Desert Storm, designed to mimic the flash of electricity from a nuclear bomb. The Sandia National Laboratory had built a 23,000 square meter laboratory on the Kirkland Air Force Base, 1989, to house the Hermes 2 electron beam generator capable of producing 20 trillion watt pulses lasting 20 billionths to 25 billionths of a second. This X-ray simulator is called a particle beam fusion accelerator. A stream of electrons hitting a metal plate can produce a pulsed X-ray or gamma ray. Hermes 2 had produced electron beams since 1974. These devices were apparently tested during the Gulf War, although detailed information on them is sparse. Mighty Oaks, 1986. In April 1986, just before the Chernobyl disaster, the U.S. had a failed hydrogen test at the Nevada test site called Mighty Oaks. This test, conducted far underground, consisted of a hydrogen bomb explosion in one chamber, with a leaded steel door to the chamber, 2 meters thick, closing within milliseconds of the blast. The door was to allow only the first radioactive beam to escape into the control room, in which expensive instrumentation was located. The radiation was to be captured as a weapon beam. The door failed to close as quickly as planned, causing the radioactive gases and debris to fill the control room, destroying millions of dollars worth of equipment. The experiment was part of a program to develop X-ray and particle beam weapons. The radioactive releases from Mighty Oaks were vented, under a licensed venting, and were likely responsible for many of the North American nuclear fallout reports in May 1986, which were attributed to the Chernobyl disaster. Executive summary of the Mighty Oak test. On the morning of April 10, 1986, the U.S. Department of Energy (DOE) conducted a nuclear weapons effects test at the Nevada Test Site, NTS, Figure 1, for the Defense Nuclear Agency (DNA), an agent for T&E Department of Defense. The test, Mighty OAK, was conducted 1,300 feet below the surface of Rainier Mesa in the T-Tunnel Complex, Figure 2. Mighty Oak was a successful test from the perspectives of both the experiment data returned and containment. There are, however, two major issues related to the execution of the Mighty Oak test: the perceived lack of containment of radiation and loss of equipment within the tunnel complex. From the standpoint of containment, there was no accidental release of radioactivity to the atmosphere whatsoever. All radioactivity was contained within the tunnel complex until April 16, when the first controlled purging of the tunnel took place. Purging is a process wherein the air within the tunnel complex is mechanically ventilated, pumped through filters, to the outside environment to remove noxious and possibly explosive gases. Such purging is carried out routinely following Eaton Tunnel test, conducted at the NTS to facilitate safe re-entry of personnel into the tunnel. Mighty Oak purging resulted in a known amount of radioactive noble gases being released in a controlled manner to the atmosphere, well within guidelines. The U.S. Environmental Protection Agency, EN, prepared a report asterisk that provides off-site radiological information gathered during purging operations. The maximum dose any person would have received standing in the open downwind for the entire period of purging would have been 0.27 microrem. This dose would have been equivalent to less than 1.5 minutes of extra exposure to natural background radiation at that same location. From the standpoint of data recovery, Mighty Oak was successful. Approximately 85% of the data from prime test objectives was recovered. However, only 70% of the overall data was recovered. Most equipment experiment, diagnostic, and construction within the tunnel complex was lost. TMS loss occurred as a result of high temperature and radiation. Other positive experiments and data were recovered. Loss of normally recoverable and reusable equipment was approximately $32 million. High-Frequency Active Auroral Research Program, HAARP, is based in Gakona, Alaska. It is designed to understand, simulate, and control ionospheric processes that might alter the performance of communication and surveillance systems. The HAARP system intends to beam 3.6 gigawatts of effective radiated power of high-frequency radio energy into the ionosphere in order to generate extremely low-frequency ELF waves for communicating with submerged submarines, conduct geophysical probes to identify and characterize natural ionospheric processes, so that techniques can be developed to mitigate or control them, generate ionospheric lenses to focus large amounts of high-frequency energy, thus providing a means of triggering ionospheric processes that potentially could be exploited for Department of Defense purposes, electron acceleration for infrared, IR, and other optical emissions which could be used to control radio wave propagation properties, generate geomagnetic field-aligned ionization to control the reflection/scattering properties of radio waves, use oblique heating to produce effects on radio wave propagation, thus broadening the potential military applications of ionospheric enhancement.